Today we'll begin looking at probability. So when we're talking about probability, a probability experiment is one in which we do not know what any individual outcome will be. But we do know how a long series of repetitions will come out. For example, if we toss a coin, we do not know what the outcome of a single toss will be. It's either going to be heads or tails. But if we repeated it over a series of time, it'll come out that half of them will be heads and half of them will be tails. The probability of an event is the proportion of times that the event occurs in the long run. So for a fair coin, that is one that is equally likely to come up heads as tails. The probability of heads is 1 out of 2. Probability of tails is also 1 out of 2. Now we have something called the law of large numbers that says as a probability experiment is repeated over and over and over again, the proportion of times that a given event occurs will approach this probability. So like we said, if we just toss a coin once, it's either heads or tails. And even at 5 times, we may not have half heads, half tails. But if I do it 10,000 times, the proportion of heads and the proportion of tails would be half and half. Now, when we talk about probability, one thing we need to think of is our sample space. Sample space is the collection of all possible outcomes. So describe the sample space for each of the following. Toss of a coin. Well, the sample space is just heads and tails. Those are our only options. The roll of a die. So we're talking about a normal dice. It's 1, 2, 3, 4, 5, or 6. Selecting a student at random from a list of 10,000 students, so 10,000 at a large university. Well, the sample space is all of those 10,000 students. So every student makes up that sample space. So we have 10,000 items in the sample space. All right. Now let's talk about a probability model. We're often concerned with occurrences that consist of several outcomes. For example, when rolling a die, we might be interested in the possibility of rolling an odd number. Rolling an odd number corresponds to the collection of outcomes 1, 3, and 5 from the sample space 1, 2, 3, 4, 5, 6. So in general, a collection of the outcomes is called an event. Once we have a sample space, we need to specify a probability for each event. This is done with a probability model. We use the letter P to denote probabilities. For example, if we're talking about a coin landing as heads, that would be P of heads. That's the probability of landing a head. In general, if A denotes an event, the probability of an event is denoted by P of A. That's the probability of that event happening. Now, when we talk about probability, the probability of an event is always between 0 and 1. In other words, for any event A, our probability is going to be between 0 and 1. If that event A cannot occur, then the probability would be 0. If that event is certain to occur, there's no doubt, probability of that is 1. Now, if a sample space has n equally likely outcomes and an event has k outcomes, then the probability will be, so we've got the number of outcomes of A divided by our sample space. So that's going to be k over n. Whoops, you didn't see that. Oh, sorry. the number of outcomes of A divided by our sample space. So K is the number of times that event A can occur divided by our total sample space. So in the Georgia lottery, a winning number between 0000 and 9999 is chosen at random, with all the possible numbers being equally likely. What is the probability that all 4 digits are the same? Well, let's think about what our event is. So the probability that all 4 digits are the same. We need to think about how many ways that could occur. Well, we would have 0000, 1111, 2222, and so forth, all the way down to 99999. That's actually 10 ways. Now, how many total possible outcomes we would have would be 10,000. So our probability is 10 out of 10,000. So the probability of that event is going to be 0.001. Now, when we are sampling an individual from a population is kind of like a probability experiment. The population is the sample space, and members of the population are equally likely outcomes. So let's take, if we have 10,000 families in a certain town, categorized as follows. A pollster samples a single family from this population. So we have a total of 10,000 in the population. What is the probability that the sampled family owns a house? So the probability of owns a house. How many people owned a house? Well, that's 4,753. Out of how many families were there? 10,000. Now on the homework, sometimes they leave it as a fraction and sometimes they leave it as a decimal. If I divide that, I get 0.4753. The next one is, what is the probability that the sample family rents? Oh, now we got to be careful here. They rent. Well, renting is not just renting a house or renting an apartment. That would be somebody from either one of those groups. So I would add those two together and then divide by the 10,000 total people. So that's 3,769, yes, out of 10,000, which would be 0.3769. Now, an unusual event is one that is not likely to happen. In other words, an event whose probability is really small. There are no hard and fast rules as to just how small the probability needs to be before an event is considered unusual, but we follow this rule of thumb. Usually our cutoff value is 0.05. We consider anything, if the probability of the event is less than 0.05, then A is unusual. So in a college of 5,000 students, 150 are math majors. A student is selected at random and turns out to be a math major. Would that be an unusual find? So probability of being a math major, we're going to take 150 divided by 5,000. Now this one I do need a calculator for. The other ones were pretty easy. So I'm going to take 150 divided by 5,000, and that's 0.03. Now that is less than 0.05, so this is unusual. Now, the law of large numbers says that if we repeat a probability experiment a large number of times, the proportion of times that a probability outcome occurs is likely to be close to the true probability of the outcome. The empirical method consists of repeating an experiment a large number of times and using the proportion of times an outcome occurs to approximate the probability of the true outcome. In a recent year, there were 2,046,935 boys and 1,952,451 girls born in the US. Approximate the probability that a newborn baby is a boy. Well, first we need our total sample space. Well, our sample space is going to be the total number of babies born. Well, that would be to add those two together. So 2,046,935 plus 1,952,451. And that's our total number of births. So the probability of having a baby boy would be the 2,046,935 divided by the total number of births. So 2,046,935 divided by, and I get 0.5118. So the probability of having a boy is approximately 51%. And that makes sense because there's pretty much a 50-50 chance on having a boy or having a girl.